So, okay, why is my... Right, we're up. Okay, quick note on Group SCS. I founded the business, co-founded the business 30-something years ago. We're one of the major contractors in smoke control. We work on many of the larger projects in London. And we're a manufacturer of control panels, dampers, and other things, smoke control. Sorry, okay. So the presentation, I've tried to split it into manageable chunks, so it's not to lose you in it. We start with looking at the design standards that apply and the decisions on which areas need to be pressurised. We then look at the system. I mean, obviously, to pressurise, we need to put air in, and we look at how we get the air in. We then, almost as importantly, need to get it back out again. And then we look at the standards for the system components and what you need to look for there. And then we wrap up with good practice in installation, commissioning and handover. And throughout, I've tried to identify the areas where you can find more information. So relevant clauses in the standards and codes of practice, which should help you in the future when you need to find something quickly. So the design standards and the areas to be pressurized. So what we're doing with pressurization is we're creating a barrier for smoke to prevent it entering the escape route. And we basically do that by two ways. Firstly, by creating a pressure difference. So if you imagine a tyre or a football, if there was a puncture in it and we were pumping air into it, we could keep it at a standard pressure if the air being put in equals the air coming out. And that's more or less what we're trying to do with the pressure, is we're putting air in, letting it escape and managing that balance. So we create a pressure differential across the building. The second part is when a door's opened, then it's impossible to maintain that pressure, and then we need to do something different. And then we create a velocity, an average velocity across the doors onto the escape route to just again stop the smoke getting into the escape route and keeping the staircase clear. To design the system, and I'm not really going into any detail in design today, we look at all of the routes, all of the leakage paths across the building, and identify those, measure, if you like, and aggregate them and decide what pressure we need to put to overcome, what airflow we need to put in to overcome those leakage paths. So why is pressurization making a comeback? The fact that you're all here means something has changed. Back in the early days, and I mean, I've been in smoke control for about 40 years, sadly, pressurization was very common until smoke shafts became possible, and that was in about 2002. People started using smoke shafts instead. Before that, it was either automatic opening vents to outside or pressurization. So we did a lot of pressurization systems in the 90s and the early 2000s, but then it pretty much died a death, and you know, very, very rarely come across it. But the impending changes to BS9991, the standard for the code of practice for residential buildings, it was out for comment last year, and they're in the process of incorporating the comments now with a view to it being published later this year or early next year. And there are some significant changes in that. The main one being that evacuation lifts and lift lobbies are required in all buildings that require a lift. Secondly, the standard recommends that natural smoke ventilation should only be used for multi-stair residential buildings up to 30 metres. And then the third part is it says that pressurization is the only acceptable smoke control method for single-stair residential buildings over 18 metres. So as a result of that, people are rapidly redesigning their buildings, adding in lift lobbies, and then adding in pressurization systems to protect them. So the current standards are slightly confusing. The new standards were released last year, 2002. BSCN 12101 Part 13 is a standard for design and installation and commissioning. And then BSCN 12101 Part 6 is now the specification for products, really, for kits. So that standard puts together kits of parts, for example, a fan, a control panel, an inverter, and an air relief vent, and then specifies a test rig and a method for testing those to test for example, reliability and response time. But confusingly, that replaces the 2005 version of Part 6, which covered the whole system, product and design. And that standard's now been withdrawn. And then a further slight complication is that neither of the new standards are harmonized standards, which means that third-party certification and testing is not required for them. I'll cover this a little bit more as we go along. So basically, these are the current standards which you need to design to, but testing to them is a slightly different matter, which we'll discuss. The pressurization classes, the standard simplifies things a lot, and it just says there are two classes: Class 1, which is for means of escape, and Class 2, which is for firefighting protection. And that is for buildings, depending on the country where you need firefighting protection. So in the UK, that will typically be buildings over 18 metres, will be Class 2. The standards are, the classes are identical apart from the open door air velocity. So the airflow velocity is 1 metre per second for means of escape conditions, 2 metres per second for firefighting. Then, unfortunately, there's a national annex to the standard where the UK have put some additional conditions in, which confuses the matter slightly. So the national annex discusses the old classes, and there used to be 6 classes, and kind of implies that they were still very useful, and they'd like some of those conditions to still be included in the UK. So we have a new standard and then a national annex, which makes additional recommendations to the standard. The main ones I'll discuss next. They're not too onerous, but it does make things slightly more complicated than the wonderfully simplified standard as published. So the areas to be pressurized, the national annex recommends that there are 3 examples out of about 14, I think, that should be used in the UK. So essentially, these are the 3 conditions that you're likely to come up against. So we have example 8, which is for buildings without firefighting lifts. And for this one, we're pressurizing the staircase, pressurizing the lobby, and we're having air relief within the corridor. We then have example 7, which is a very simple building with 1 accommodation door off the lobby. And in this case, we're pressurizing the staircase again. We're pressurizing the lift shaft, the firefighting lift shaft, and we have air release from the accommodation. And then this is probably the most common scenario that you're likely to encounter, which is all of the cases, certainly for buildings require firefighting protection. We're pressurizing the staircase, pressurizing the firefighting lift shaft, pressurizing the lobby, and then we have air relief from the corridor. And that's certainly the most common system that we provide. So looking at the performance criteria for the system, there are generally 4 main criteria that must be met. And if you're involved in assessing systems, these will be the 4 things that you measure at the end of the job to prove that it meets the standard. The first one is the pressure differential, excuse me, which is 30 pascals in the current standard, which is reduced from 50 in the old one. So we have a pressure difference between the accommodation and the stairwell of 30 pascals. The second performance criteria is the open door velocity. So when we have doors open, the pressure characteristic is lost, and then we move on to the open door air velocity. So we need an average open door velocity across the door from the stair to the accommodation or from the lobby to the corridor usually, of 1 metre per second for a Class 1 system and 2 metres per second for a Class 2 system. The 2 metres per second is the same as the old standard, but the 1 metre per second is slightly higher. The old standard, you'll remember, used to be 0.75. The third performance criteria is the maximum force required to open doors on the escape route. Now, if we put too much pressure in there and the pressure rises too much, then that can make doors really difficult to open. So there's a limit on that of 100 newtons. So the maximum force required to open the doors is 100 newtons. Sometimes on buildings where there might be less able people, then that can be reduced to 30 newtons. Sometimes the 30 newtons only applies in normal use and not in firefighting conditions. So that's not 100% clear. So it's worth clarifying whether the design is for 30 newtons in fire condition or 30 newtons in non-fire conditions. And the last criteria is are the response times. So the response times are the same for both types of system. So we have an initiation time of 60 seconds, which is the time from receiving an alarm for the system to start to operate. The operation time of 2 minutes, which is the time taken to get to the deployed position, if you like, so that the pressure differential to be in place. And then we have a response time of 5 seconds, which is the response to a change in condition. So if a door opens, then we have 5 seconds to get up to the open door velocity. If the door closes again, we have 5 seconds to get up to the 30 pascals pressure difference. So so showing them diagrammatically, for a Class 1 means of escape, generally up to 18 meters, we have 30 pascals pressure difference with the doors closed, 100 Newton door opening force, 1 meters per second open door velocity when the doors open. And then for firefighting, we have the pressurization 30 pascals. Typically, we'd have a firefighting lobby, which would also be 30 pascals pressure differential, and we'd have a lift shaft, a firefighting lift shaft, and possibly an evacuation lift shaft, also pressurized to plus 30 pascals. The open door velocity, and this is where the national annex comes in. For the 12101 part 13 doesn't mention open door conditions, which doors are open when you test the open door velocity. It just says you need to get velocity across these doors, but it doesn't specify if any other doors would be open. The old Class B used to specify other doors to be open and to sort of mimicate firefighting. And the annex, National Annex A, recommends that this is the case for this. So for the 2 meters per second open door velocity, we have the door from the stair to the lobby, the door from the lobby to the corridor open. We have the lift door on the firefighting lift on the floor below the fire floor open. We have the lobby door on the floor below the firefighting floor open. And we also have the door at ground level into the staircase or fire service access point into the staircase open, which is quite a bit different to just providing it across that door. So we need quite a lot more air to achieve that. So moving on to the pressurization air delivery. So the stairwell first. So we're providing air into the stairwell to pressurize the stairwell. There might be two speeds for this, so it might have to. It's possible to have the system that it runs at means of escape duty initially, and then the fire brigade can switch it up to firefighting duty when they arrive. It's better if it works automatically, in my opinion, but there's a possibility that it would have two speeds. It needs to be ducted with injection points at every third level. So unless you can prove in a design that it'll work with less. So you might be able to model it to prove that you need less injection points, because obviously getting a duct down the stairwell is not the easiest thing. We then look at the lobbies. So where we're pressurising lobbies, they'd all be pressurised simultaneously. We wouldn't bother just trying to pressurise individual floors. We'd pressurise the whole of the building. And the lift shaft would also be pressurised. Again, the standard says the firefighting lift shaft shall be pressurised. It doesn't mention evacuation lifts. The National Annex says that it may be required or may be beneficial to pressurise firefighting lifts as well. But again, there's no hard and fast rule on that. The lift shafts are pressurised with a single injection point at the top usually. So these pressures, the air delivery to these areas is generally static, so it doesn't need to change speed because the open door velocity comes from the stairs. So that can be dealt with, and quite commonly is with one fan set and a separate fan set for the stairwell. Well, then we move on to air release because we need to get the air out of the building. So obviously there needs to be an airflow path to outside, otherwise everywhere would just equalise and we wouldn't have a pressure differential. Air release is probably the most common cause of problems in systems because there's always pressure to reduce the space taken up by plant and shafts and ventilators, and it's quite often the area where there's inadequate provision, and there's not much you can do about it if it's not put in right in the first place. So if there's insufficient air release, then the pressure will build up, and we'll have this problem where you can't open doors onto the escape routes, which is the last thing you need. And the areas required are quite big, certainly for firefighting protection. So a typical airflow rate through a standard door for means of escape would be roughly 1.8 meters cubed per second, which would equate to an air release vent area of 0.6 square meters. For firefighting, we're looking at double, so we're looking at 1.2 meters squared area of vents, somewhere of that order. You know, it depends on the size of the doors, etc., and what velocity you think you can get away with. So you definitely need a dedicated provision for firefighting vent. I mean, it is possible sometimes to get the air release through natural ventilation and leakage sometimes for means of escape condition. So it's possible to create this with automatic opening vents or windows. They need to be in at least two faces of the building and preferably opposite each other. And that means you need to provide the total area in each side of the building. It's not half and half to allow for adverse wind pressure. If we're using this method, then the ventilator should comply with BSEN 12101 Part 2, the natural heat and smoke and heat exhaust ventilator standard. But more commonly, the air release is provided via a vertical shaft. And then this can either be natural or mechanical. So for natural air release, we've got a shaft of about a meter squared or maybe slightly larger. An air release vent at each floor into the shaft, and then a vent at the roof out of the shaft. The air release works only on the flyer floor, and it works via smoke detection within the corridor or the lobby. If we have a mechanical shaft, it's typically half the size, but we have to have a fan set on the roof. And positioning that can be tricky because if the supply fans are also on the roof, then there's a danger of the extract fan, extract ductwork, the same as a natural vent, to be honest, contaminating the inlet of the pressurization fan and recirculating smoke around the building. So siting all of this equipment is a bit of a task. And then the last part of the puzzle is the pressurization air relief, not to be confused with air release. And this is because the volume flow rate to achieve the open door velocity is a lot more than to achieve the pressure. So we're blowing a lot more air in than we need, and it has to go somewhere. So essentially, when the lobby doors are closed and we just need the pressure, then either we have to slow the fan down or we have to do something with the excess air that's being put in. So the most common way of doing this is a pressure relief damper, where we'd have the damper would be closed when the door is open. We provide the airflow velocity, so the damper closes, forces all of the air through the lobby door, and we get this nice 2 meters per second velocity. When the doors are closed, then the damper reacts to that and opens, and the excess air goes out through the pressure relief damper. We typically use a penthouse. These are gravity operated, calibrated to the maximum pressure, and they just open and close depending on the pressure within the staircase. The other option is to monitor the pressure difference between the stair and the lobby and modulate the fan accordingly, so that when the doors open, the pressure sensor will note that the pressure's dropped and increase the fan so that we get the velocity. And then conversely, when the door's closed, the pressure will rise and the inverter will slow the fan down. And this is possible. However, with a 5-second response time, it's quite difficult to achieve, but it can be done. So in summary, this would be a typical arrangement for a firefighting system on a high-rise residential. So we have our fan set in the stairwell, pressure relief vent, and then we have one fan set catering for the lift shaft and the lobbies, and a natural air release shaft with a vent at the roof level. A note on extended travel distances. If we have an extended travel distance on a residential building, on a high-rise single staircase building, then we need to protect this corridor as well as the lobby. So we have an extra, if you like, an extra system to accommodate. And this is what the system was likely to look like. We have the standard pressurization setup, where we're supplying air to the stairwell, to the lift shaft, and to the lobby to raise the pressure. And then within our extended corridor, we'd have two shafts. So we'd have an air release shaft, which would also be, if you like, a smoke extract shaft for the corridor. So typically that would be mechanical and would keep the corridor clear of smoke. And then we'd have an air supply shaft at the opposite end of the corridor, which could be natural or mechanical, which will, if you like, flush the smoke through the corridor. So something like this, there's an awful lot of equipment to put on the roof, because we've run a standby fan set here, another one here, another one here, and a natural or a mechanical inlet shaft. So over and above what we currently supply, which is one extract shaft, this is quite a big difference. And this would need a CFD model to prove that it'll all work together. Okay, so if we move on to the components of the system, I mentioned the new Part 6 for kits. Now, the kit tests, I don't think there are many UK companies who have tested their equipment to the kit standard, but there are some European manufacturers who have. But in the meantime, we would suggest that in terms of complying to a standard, the individual components still in the kit, if you like, still need to comply with the harmonized standards, which are the 12101 series. So we would recommend that you, for the time being, focus on compliance with the 12101 standards and look for declarations of performance against that standard. So looking at the parts of the system, so the fan units for the air inlet are ambient temperature, so there's no third-party 12101 test required for that. They need to be run standby, and the preference is to locate them at ground level, so it's not possible for the inlets to become contaminated. Sometimes they can be put in a basement if that's easier. If they're located on the roof, then the inlet must be arranged to prevent smoke contamination. So what typically happens is there'll be a T-section with two inlets running to opposite sides of the building. And then there's in-duct smoke detection such that If smoke's detected in one inlet, then there's a damper that shuts off that leg. If smoke's detected in both of them, then they both shut off. But the smoke detection must be automatic resetting. So when the smoke has subsided, then the fans will restart. If we use a mechanical air release, then they are high temperature fans tested to 101 part 3. And the ratings would be F300 for sprinklered buildings and F600 for non-sprinklered buildings. Again, they need to be run as standby, and the discharge needs to be located where it can't contaminate the inlets, which is difficult. So for air release ventilation, the air release shaft, typically a shaft, if we have facade vents, then they're 12101 part 2 smoke vents, because they're a single compartment. If we're using dampers into a shaft, then they need to be smoke control dampers tested to BSEM 12101 part 8. The air release shaft should also ideally be tested to EN 1366 part 8, which is the ductwork standard, and classified to the same rating as the compartment which it passes through. Commonly, shafts constructed from Class A1 materials will be acceptable, and that's probably more common than a proprietary tested smoke shaft system, although there are some around. For the air supply shaft, where it's sited in one compartment, which would typically be the staircase, it can be standard ductwork or builder's work. But where it passes through compartments, typically in a lobby, then it needs to conform to the BSEM 12101 part 7, which is the ductwork standard, and again classified to suit the compartment through which it passes. But here again, builder's work constructed from Class A1 materials is commonly used and commonly acceptable in the UK. And then the control system, usually it'll be well, almost always will be a programmable, addressable system. And it should operate automatically from the fire alarm system or a dedicated smoke detection system. It needs standby power from a separate supply with an automatic transfer switch, which complies with BS 8519. Control panels should comply to ISO 21927 part 9, which is the equivalent of BSEN 12101 part 9, which is a non-harmonized standard. So that is another one that would require self-declaration rather than third-party testing. But it is a useful standard, and it does cover things like cable monitoring and some other really useful points. So it should be specified wherever possible. Power supplies should comply to 12101 part 10 and should be third-party certified to that. We should also have a fire service control at the access point. The fire service are increasingly reluctant to use manual controls and would much prefer systems operate automatically. However, the standard does suggest that a simple fire override switch with auto on-off positions should be provided at fire service access point. There should be a manual control option for testing and maintenance as well. And then all cabling should be to BS 8519, typically category 2 for means of escape systems and category 3 for firefighting systems. So looking at the kind of installation and handover next to wrap up. BS7346 part 8, which is the code of practice for planning, design, installation and commissioning and maintenance of smoke control systems, all smoke control systems, not just pressurization, is a rarely used standard, I think, or I rarely see it specified, but it's excellent for managing the process of installation. It goes right from identifying the requirements right through to maintenance and servicing. It's got lots of good templates, lots of requirements on competence, and is just a really, really good document for ensuring that a project is managed correctly. So I would highly recommend specifying this and using this wherever possible for managing the competence of contractors. Talking of competence, we also would suggest that third-party certification should be a minimum requirement for smoke control and any other life safety system. The IFC SDI 19 is the only third-party certification scheme for smoke control contractors. Within the scheme, there are 4 membership categories, level 4 being the highest, and level 4 would be required for pressurization systems. And I would be careful if you're selecting contractors or approving contractors, because, as I said, most of the newer entrants to the market will have no experience of pressurization systems, because, as I say, for the last 20 years, they probably haven't really been used very much. So I would tend to use one of the more established companies if you are involved in pressurization systems. So moving on to commissioning and handover, it takes a long time to commission a pressurization system. So one of the things I would suggest is that you try and get the process started as early as possible. But the problem is the building needs to be complete prior to carrying out testing, which means the finishing's complete, carpets down, doors are all on, and it being decorated and all finished. So it's very difficult to get enough time to do this properly. And we need to do a lot of measurements on each floor, and there's a lot of walking up and down stairwells, changing something, walking up and down again. So it is kind of an iterative process. So we need to take measurements on every floor and record them, which would be, as a minimum, the pressure differentials, the open door velocities, door opening forces, and the response times. We would always, and we always have, carry it out at night when there's nobody in the building, because once people open doors further down the building, it puts all of the readings out. So you need to get a good run at it to be able to do a full set of readings without the building being disturbed. Annex H of 12101 Part 13 contains a really good template test report. So if you have nothing else available, I would recommend that you use that. And we would then expect a full cause and effect test, where we test every point on the system using the live system. If there are any other systems that are being used to trigger it, sprinkler flow switches, fire alarm system, that the test is live from those systems before accepting the system. And then for a demonstration procedure, we would recommend that clause 8.5 of Part 13 details the test methods that should be used, and we would expect that there would be a full comprehensive set of documents available before carrying out any witnessing. If that's the case, then we would suggest that sample floors can be witnessed. Again, Part 13 recommends that the top and bottom floors are tested and verified, and then intermediate floors with a maximum of 3 floors between test floors. So depending on the height of the building, we would be sort of testing every 4th floor between the top and the bottom. And again, we're just comparing it with the commissioning results to make sure that it all makes sense. The equipment you would expect, or you would definitely need to carry out this demonstration, would be a calibrated vane anemometer, a manometer, a stopwatch, a door force gauge, and a smoke detector tester as a minimum. So we would typically run through this with the start with the system at rest. We do the fan checks first, demonstrate the main fan running, fail the main fan, check the indication on the control panel, check the standby fan cuts in, and we'd also ensure that there's fan test data available for both fans, so the system has been tested with the standby fan, which is not always the case. We then run through the power checks, simulate the power failure, make sure that the standby power cuts in, and check the switching time and confirm that that's within the limits. And then we'd run through a cause and effect on every floor, starting by testing the automatic operation. Then we test the manual override, check the volume readings, pressure differentials, door opening force, and record the response times and make sure there has the commissioning data. And then lastly, the documentation that you would expect to be provided with the system. Clause 10 does a really good job of specifying what documentation should be provided, which includes a design report, including all the calculations, a full set of test results, a commissioning certificate confirming compliance with the relevant standards, operation and maintenance instructions, including as-built drawings, and declaration of performance for all relevant products, and installation certificates confirming the mechanical and electrical installation has been completed properly. And then once the system's been finally installed, again, the standard recommends a test regime. So it suggests that daily we should be checking for faults and also checking that any faults noted the previous day have been rectified. Monthly, it recommends that the system's operated for at least 10 minutes, checking the fan operation and at least 10% of the components. So 10% of air release dampers, for example, with all components being tested in a year. And then also to check the power supplies, standby power supplies, check batteries, etc. So that's the monthly tests, which could be by a trained in-house personnel or a specialist. And then yearly, there's a performance check that needs to be completed by a specialist, which is fully detailed in Clause 8 of Part 13. Here's it's probably a bit difficult to read, but I can send you a copy of this if you want. This is a summary of the regulatory testing requirements, if you like, through mainly BS 9999, but also the new fire safety regulations. So the fire safety regulations have put in some additional requirements for high-rise buildings, high-rise residential buildings, over 18 metres containing 2 or more flats. So the requirement is to carry out a test the system under fire alarm and also under manual fire brigade override if there is one, and confirm the system is operational. The test must be recorded and the results available to tenants of the building. And if there's any fault, that must be recorded. And any faults that aren't able to be rectified within 24 hours must be notified to the fire and rescue service. And they must also be informed when the fault has been rectified. And additional signage should be placed on the defective fire safety equipment to notify people that there is a fault. So that's a very new requirement that I'm not sure how, if that's actually been actioned much yet. That came in January. So that's it for the presentation, more or less. I would say in summary, accommodating the equipment really is difficult. And it's impossible as an afterthought. So you really should be undertaking the design of the system as early as possible, and don't bow down to pressure to make things smaller than you think you need, because it will come back to haunt you. And then also to check competence of contractors and ask for reference projects for pressurisation, because, as I say, there aren't many around. And then also to use BS7346 for implementation for all systems, not just for pressurisation, and particularly for commissioning and handover. And that's it. So I'll be happy to take any questions. Thank you very much.
Well, thank you very much, Alan, for that that synopsis and presentation there. There are a couple of questions that have been raised. The first one is a very well, one that I think all of us in the industry is waiting for. When is BS9991 going to be published? Do you know?
I don't know. I wish I did know. I've heard various rumours that it might be this year, but it might be into the first quarter of next year, and I honestly can't be any more definite than that. It's very frustrating.
Yeah. Yeah. I mean, it's I think they've put it out there. Now, of course, approved document B is out as a draft, and there's a decision has to be made as to, is it 2 stairs, is it 1 stair? I think the fire brigade have made their point extremely clear as to what they're looking for, and it may, you know, once the approved document, you assume, has been agreed, then the British standard will either be tweaked to reflect it, or will be published in full. Which, yeah, so I think that's probably where we're waiting. Another question.
Go on.
Sorry.
No, I was just saying, if there's a big difference between 9991 and ADB, that's going to be very confusing, isn't it? If 9991 says one thing and ADB says another, and you can take an easier route by using ADB but contradicting 9991, I don't know how that'll play out, really.
Well, probably the government wouldn't want to go down that line, so they're probably waiting to deal with the consultation and approved document B, and then from that, 9991 would probably support, you know, the minimum standard in approved document B. And as always, 9991 would be a bit of a higher standard. And if I'm right, I think the Health and Safety Executive and the Fire Brigade would always want you never to design to the minimum standard, but to always look at a pragmatic approach in your fire safety design and go for the ultimate best scheme. Closely followed by a QDR as to the reasoning behind the decisions that's been made. So, yeah, it's an ongoing story, I think. Another question is, why is natural smoke venting no longer sufficient on tall residential buildings? And again, it goes on to say, will there be a change to approved document B?
Yes, I've no idea, because there just seems to be a general movement away by the fire and rescue service from natural ventilation. But I mean, I as I said, I'm old enough to remember the original report on natural shafts, which was I think in 2002, and that suggested that they were fine up to 99 stories, as I remember, a natural shaft. There are limits. I think 99 stories was probably too high, but I think for, you know, a lot of buildings, a natural shaft is a perfectly acceptable route. But I think there's no way back from this. They're definitely trying to wean it out, and particularly automatic opening ventilators, even more stringent. I think the places where you can use those are likely to be even less than for natural shafts. I think it's irreversible, but I'm not really sure of the. I think it's probably a bit of an overreaction. Is my personal view on this, but that's just my view.
Okay, so obviously, I presume it's also very much dependent on the weather. I mean, obviously, if it gets really hot outside and it's hot inside, then you're not going to get a buoyance of air, and so you won't get a difference in air pressure. So your natural smoke venting is very much reliant on air coming over the top of the shaft to draw the heat out. And if there isn't that movement, that's a problem. Other problems is the buildings are built so close that by the time the plant room gets on top of the roof, the 2.5 meters away from the opening shaft tends to be questioned, as well as being 500 above and not being obstructed. And most people, I find, they put in their smoke shaft and then they realise, oh, but that's not an obstruction. Yes, it is, and it potentially blocks the wind from blowing over the shaft, and so yeah, that may also be a reason why natural isn't always the best.
Yes, yeah, I think for very tall buildings, you're right. But,
one person has very put down it's a very cheeky question he's asked for, but he goes on to say, are you aware if there are going to be any limits on single stair building heights with a pressurized system in BS7991? He goes on to say, obviously aware of approved document B consultation looking at removing single stairs as an option above 30 meters. there's potentially 2 pressurized stairs lobbies would then be required, which is a lot of floor space being used and a large number of shafts. Can stairs potentially share a pressurized system? Would this be practical? So that's actually in the chat if you want to have a look, because he was very kind enough to write a bloody essay.
Yeah, yeah. There definitely is. There definitely is. You know, it's unlikely that single staircase buildings over 30 meters are going to be permissible. It seems that there's definitely a movement away from that. With regard to systems, there would need to be a separate system for each stairwell, unfortunately, and they need to be independent. There might be some possibility of sharing an air release path if in the sort of central corridor, but the standard is pretty clear that systems for separate stairwells should be independent of each other. And it is an awful lot of equipment to fit into a building.
Following on from the previous conversation we had, another question's been raised. If 2 staircases are adopted, do you think natural ventilation could then be reconsidered in place of pressurization?
Well, yes, it can, but they put a 30-meter limit on it in the current version of 9991. So you can use natural ventilation, but only up to 30 meters. So on a multiple staircase building, up to 30 meters.
Okay, so I have a question. And pressurization, you have a building that's been pressurized, it's in a fire situation and people are escaping. The fire brigade then turn up and decide that they want to evacuate 2 floors using the new emergency evacuation system. How does that affect when you have 2 doors on a staircase opening and the pressurization system? Does that then, because the pressurization is just relying on a fire on 1 floor and it working out on that basis. Where you now have more than 1 door onto the staircase being opened, because truth be told, if you have 5 fire engines turning up to a block of flats, I'm almost certain everyone in the block of flat will decide it's time to leave, and will all leave at the same time, regardless of the fact that it's a stay put. And so with all of that, you know, that's perception of the public. You see 5 engines turn up, you're going to be the first one out of that door and downstairs.
Yeah.
How does that leave pressurization then when you have all these doors opening when you weren't designing it to be opened?
Yeah, it is an issue, and there are some conversations in the industry about whether there needs to be a different open door velocity regime where we test different things. But it's not as bad as it sounds, because we're already testing with the ground floor door open to atmosphere and the lift shaft door, the lift door on the floor below, and the door into the lobby on the floor below, plus the fact that the lobbies will be pressurized. So if we're opening a door into the lobby is pressurized, so there's no path, air release path. So the air is not all escaping necessarily, it's going into a pressurized lobby. The only place where you're really losing air is on the fire floor, where we've got the air release path open, and the ground floor door where it's going to outside. So the other ones, although they will have an effect, it won't be as dramatic as you would imagine, because there's no path to atmosphere from those floors.
Okay. So from that then, my next following up question would be, do you have to do a CFD model to justify a pressurization system?
No.
And if so, you don't have to. Okay, because that will save a fortune.
You would if you have an extended corridor and you have and you're trying to protect the corridor as well as the firefighting lobby and the staircase, then you probably need to model that to prove that all of those things work together. But for a standard system, it's usually calculated by a spreadsheet, and the fire is irrelevant almost. It's not as though we're designing for a fire or have any fire modeling, because all we're doing is delivering a volume flow rate and a pressure difference it's kind of disassociated from the fire, if you like. Somewhere somebody did some research and came up with 30 pascals and 2 meters per second and 1 meter per second, and in that case it's just an M&E system. It's not really a fire, you know, in the sense of the old black magic of smoke shafts and you know, shopping centre designs, etc.
Okay, fine, thank you. Now, there's a hand up. I appreciate there's a hand up. So I've got Sean Peggett. You have your hand up. Is that for a question?
Yeah, yes, please. With regard to the air release shafts, I don't have much experience with pressurization systems. I done many high-rise buildings at the heights you're talking of. You mentioned facade vents for the release. Does that, obviously you don't have to have the shaft then on the facade vent?
No, if you can do it in a facade, and that would typically be an open plan office where you can put windows on the outside. If you can provide it in 2 faces of the building, the total requirement, so say you needed 1.5 square meters, you can provide that on 2 sides of the building, then that will suffice, as long as there's a path, obviously, from the lobby to the air release vent. So, as I said, typically an open plan office. It's not really, it's difficult to do in a residential situation because you're unlikely to have a long corridor where you can have vents at each end, although you know it's possible.
I suppose the best situation would be to have a facade vent with an open courtyard design at a multi-story building, would it?
You could do, yeah, if you could. Although again, you might only be getting it in one face. If the wind can blow at one side of it and prevent it working, or then you need to have it in an opposite vent, or at least another face of the building. So it's not very often facade vents, to be honest, because of that problem of trying to find. And then the problem is if you do it in an open plan office and then they end up subdividing it, which they often do, and there's no path to the vents, then that can be a problem as well.
I was just thinking of a way of trying to eliminate the air release shaft as a cost exercise. Do you understand?
Yeah, there are occasions where we're retrofitting systems where you've got, you know, old, say 4-story buildings where the stairs open directly onto the staircase, and it's what you do with it. And we're trying to organise. In fact, I was on a call just before this, where we're actually putting air release shafts in the apartments, which is very unusual. There's 2 apartments on each floor, and we're having to put an air release shaft in each apartment, which is less than ideal. But you can do that as a, you know, if you're stuck with a building that you can't really do anything else with.
Thank you very much.
Or building control will often, you know, accept something that's better than nothing, that we're pressurising the stair, but we can't achieve the open door velocity, and that'll be acceptable quite often.
Okay, thank you.
You're welcome.
The last question that I'll take for this session here is your system offered with any UCAS approved independent third-party certification? Would it be a useful addition to your commercial offerings?
There's not really anything for the system. As I said, the kits part of the product can be tested. So you have each product is independently tested and certified. So we've got a fan, a damper, control panel. Then we put them together in the kit and test it in a test rig, and then we get a kind of an extra badge. So that would be the nearest thing, is to use kits that have been tested to Part 6, and that would be a self-declaration. You still carry out the tests, but there's no declaration of performance because it's not a harmonised standard, unfortunately. But as I say, there are kits that do meet that standard, but there's not an appropriate vehicle, I don't think, to offer that at the moment. although, you know, who knows, because as I say, they are getting more and more popular now, so it's likely to develop as we see more and more of these being installed.
Okay, 2 minutes past 6. I think we've done really well. So, Alan, thank you so much for your presentation. It was short, but it just highlighted an aspect that I think all of us now, obviously, the important part is engaging with competent professional people who can actually undertake to do this task. And I think the commissioning of a pressurization system, as you've highlighted, for me, I think that is the important aspect. The aspects that we should be asking for with regards to the commissioning certification, what is expected, and making sure we get the right documentations to say that yes, the whole system has been tested appropriately. And I think you thank you for that. Those last couple of slides, which I found quite useful. Your presentation will be handed out to members, and Rosemary will be doing that sometime later this week. So really, all that's left for me to do is thank you again for giving your time and for coming back for the second time to give us an online presentation. For the members of CABE, as I mentioned earlier, we've got our in-person conference in London on the 14th of June. Please look at the CABE website. It's a free event, but you must register to attend. If your name's not on the list at the front door, you will not come in. So please go onto the website and register. Other than that, I wish everyone a good evening, and thank you for your time and support of our region, and have a good evening. Thank you.
Thank you.
Thanks very much.
Cheers. Thanks a lot. Have a good evening.
Thank you.